flight test had a job cut out for themselves. They knew that they had to certify this airplane in the same year that the #1 airplane made its first flight. We had to take this airplane and first prove that it met the Boeing and customer requirements, and then prove that they met the FAA regulations. We had to take the first 5 airplanes off the production line and do the job in the shortest possible time.
#3 airplane utilized a long nose boom, which was used to measure gust loads during the flight load survey program.
With these 5 test airplanes, we had to select personnel to match the responsibilities assigned to each airplane.
Quite a bit of competition between the different airplanes.
This whole job started way back down the line when engineers were still looking at paper airplanes and models, and wind tunnel testing began.
Our people devote literally thousands of hours of their time, and both on paper and in the wind tunnel, to minimize drag, because drag is money. Drag costs weight, drag costs fuel.
The Iron Bird serves 2 outstanding purposes: development of the reliability of the control systems. The other is training for the flight crew.
Later on, we take 2 complete airframes and scientifically destroy them. Fatigue testing simulates the equivalent of 2 normal airplane lifetimes. Static test design limit testing must be completed before the airplane can be flown through its full design envelope. The static test airplane is eventually subjected to ultimate loads to prove the design. Finally, the airplane is destroyed to determine how much margin of safety has been built in. The #3 airplane was instrumented with strain gauges, pressure instrumentation to measure the loads on the airplane. It was also equipped with an instrumented probe to measure angles and accelerations. During more than 50 hours of flying, we measured loads during maneuvering flight, landings, ground maneuvering, and during flight through turbulence.
The purpose of the pre-flight meeting is to discuss with all the flight crew the intended plan of test and the sequence of test events that will occur during the flight. Participants include Boeing and FAA flight crews, the pilots, co-pilot, flight engineers, the flight test engineers, instrumentation engineers, and any observers from the staff or project group. In flutter testing, as in most other flight tests, we go way beyond anything that would actually be encountered in normal flight. All the complex functions of the flight test team are required during these tests, which take the airplane to its maximum design speeds for the first time.
We have accelerometers located throughout the airplane and all the control surfaces. All this is telemetered or radioed to the radio room. They're printed out on paper, and the engineers down there monitor all our parameters. They can tell even sooner than we can if everything looks satisfactory. They are the ones that give us the clearance to proceed to the next higher speed or the next condition.
This is the way we see it in the radio room, but the chase plane observer sees the real thing.
Right here I was passing from left to right, approximately 25 feet underneath the aircraft, and the main reason why I'm along on these flutter flights is to note the general condition of the airplane and also to report anything unusual, like we had initially had some problems with the vanes, and I could see them much easier than they could from within the cockpit. When we flying the airplane, this is called minimum crew testing. We just had a pilot, a co-pilot, and a flight engineer. Just 3 people aboard the airplane. We'd launch the fighter, which I was flying, and I would go up and check the atmosphere and make sure we had smooth air or could operate free of clouds. Since this is baseline data, we want to know exactly where we're standing. In other words, we don't want to have any inputs from the air. We just want to have inputs from the controls or from the vanes.
During these high-speed flutter tests, the airplane was shown to be highly stable, and we reached maximum Mach number speeds of 0.99, which is 99% of the speed of sound, and as high as 685 miles per hour, true airspeed.
One thing you'll notice about the Boeing engineering gang. Each one thinks he has an individual enterprise. The success of the Boeing company in the transport business is a result of the engineers and the shop guys feeling they're private enterprisers. And they're so anxious usually when we come off that airplane to know what happened that they're not willing to wait a half an hour for the post-flight meeting. They want to know what it is right now so that they can get going on urgent items.
We try and work very rapidly. We take the flight tapes from the airplane. While the airplane's up flying, we're doing preliminary work in getting the calibration values for all the instrumentation that's on the airplane, getting these stored into the computer and preparing to run the data when we get the tapes. When we receive the tapes, in conjunction with this, we get data requests from the analysis groups. These call out what time intervals the airplane was doing certain critical tests. Many times run the tapes, first of all, through our quick look ground station, which produces rolls of strip charts or oscillograph rolls that give analog traces that tell us whether or not the instrumentation's working right and whether or not we have any problems with the data.
The greatest change that has occurred, that is as far as flight testing is concerned, is in relation to the data handling system. The amount of information that our company today finds out about the airplane in relation to each test that's conducted. The amount of data that's obtained is fantastic. And of course, we couldn't have done this at all unless we'd had the big computers that our company saw fit to get for us.
We only had 10 months to get the job done, so we had to work around the clock in all kinds of weather. Took number 2 to New Mexico for landing performance, refused takeoff, and autopilot work. First, we thought we'd read the flight plan wrong. The place looked like a Mardi Gras.
Can't do anything about that.
The red carpet was rolled out, and the whole town was there to greet us. People were just great, but there was work to be done, and we had to get with it.
The 747 has a landing gear that is forgiving, and whereas that rate of sink in another airplane might have felt like a moderately hard landing, the 747, it will feel soft. I think it's a very forgiving airplane on landing. On all our airplanes, we have a system on the connected to the brakes that makes it possible for the pilot to apply brake pedal and not worry about skidding the wheels and then blowing some tires. This protective system is on all our airplanes, and on all our airplanes we demonstrate the operation of the airplane during landings and during refused takeoffs, with the system working and with it in various failure conditions. One failure condition is with two wheels not connected to the anti-skid system, and then we also check it with all wheels not protected with the anti-skid system and try to show performance of the airplane under these conditions.
Standing by in the radio car, I just got a call from the pilot that requested that we make a visual inspection of the aircraft's undercarriage, wheel, and tire assemblies. From that, I wait until he becomes parked on the runway center line, and with due safety respect, with the parking brake set, run down through the center line of the airplane, keeping well away from the engines, and inspect the 16 wheel and tire assemblies for overheating of the brake assemblies, possible loss of rubber from the tires and impingement upon the aircraft, fuel leaks or fluid leaks if they should occur, and just generally look at the condition of the underside over to ensure the pilot that he is safe to continue testing. Occasionally, due to various objects on the runway or faulty tire tread or a cut in the tire tread, it's possible to throw some rubber off, which may in fact become implanted in the flap or whatever. When installing these wheel assemblies, it's quite important that we torque up the axle nuts to ensure that they're all uniform and that the torque is properly applied to the tapered bearings within the wheel themselves. In the case of the 747, the final torquing is brought up to 500 foot-pounds, and then the nut is backed off slack and brought back up to 80 foot-pounds torque. This ensures that the bearings are properly preloaded and then loaded for use. Overall, I would estimate that there was 200 brakes used for the testing alone.
Wind stations are used to determine the correction factor for an actual zero wind condition, and then for any particular day you apply a correction for the actual wind conditions that are at the particular airport at the time you're going to make the takeoff.
Also, in all this testing, it's very conservative in that they always assume that you lose an engine, and for their takeoff distance, they take it to 35 feet. So it's very conservative what goes in the flight manual and what the airplane will actually do.
During the landing approach, the airplane is never flown below 30% above the stalling speed of the airplane. So there is a 30% cushion built in. The approach speed that is used and shown in the airplane flight manual then is 30% above the speed determined during the stall test.
During the more than 1,500 hours of flight testing, we tested the engines and engine systems, the mechanical and electronic systems, first beyond the normal envelope of operation and then simulating normal airline operation.
Some of us had to handle logistics problems. Like, who'd have thought we'd have to bring in a fire engine from Wichita? But the extra capacity was needed, so it had to be arranged.
An RTO is a refused takeoff, and this is where the airplane is accelerated to the V1 speed or decision speed, the engine's cut back, and the airplane is brought to a stop. The first tests that were performed at Roswell were done at lightweight. The purpose of the RTO and landing tests are to determine the actual stopping distance for the airplane. This data is used in conjunction with takeoff performance work, which was being done on airplane number 1. The information is required to establish a set of curves to be used by the airline pilot to determine the weight that the airplane can be flown off a particular airport. It ties in with runway length, the ambient temperature, the altitude, and the gross weight of the airplane.
A remote base operation is very important in as much as that you have to be ready to conduct tests in other areas other than the Boeing location due to weather and also due to the type of testing that you conduct. We always had to be ready to move into these remote bases, and we were also able to support our organization from this area with parts and in the flow of data from the location back to Seattle.
The main reason we went down to Edwards were for weather conditions. The weather's very, very good down there. The winds are very light, and they have the longest runway in the United States, over 15,000 feet of runway, plus 7 miles of overrun. The runway is perfect. It's very smooth, not much crown to it. It's been surveyed, and we've used it quite a bit, so we know a lot about the conditions down there. Even an airplane 3,000 pounds above the maximum takeoff weight, we've taken off, actually made a fuel chop to the engine. The engine was inoperative. This is to show our procedures were satisfactory. The airplane performed as advertised.
Our experience has been, I think, throughout the pilot group and with visiting pilots as well, that it is really an easy airplane to fly, an easy airplane to land. At least I'm very impressed with the inertial system and the autopilot system.
We then went out and performed and showed the FAA that the airplane hits its V1 speeds, its V2 speeds, its VRs, its liftoff, its climb gradients out to 400 feet.
I thoroughly enjoy flying the airplane. I get a big charge out of it and enjoy it. It has no bad characteristics. It's an honest airplane, and I'm not just saying that from a sales standpoint. I think it's really a good airplane from a piloting and also from a passenger standpoint.
Our effort is always to combine tests and run as many tests concurrently as we can. And this is done successfully in many cases. For instance, during drag or level flight performance determination, we can frequently run certain systems tests, such as hydraulic temperature surveys, air conditioning performance, certain electrical tests concurrently. What permits us to do this is the highly sophisticated and complete digital type instrumentation system that we use. It has enough recording capability that we can frequently, in order to optimize our testing, run several tests at the same time.
Somebody mentioned the flow of data back to Seattle, and then the point came up about surveyed runways. Well, theodolite film makes a good tie-in. Altogether, about 600 takeoffs and landings are recorded by theodolite cameras aboard the 747. We read the film, and the computer gives the engineers all the answers they need concerning airplane attitude and position relative to ground reference points. This data is critical, especially when airplanes are at remote base stations. After processing the answers, the data is called down to the remote base by phone. It's expensive testing, so we don't want to risk any repeats.
The autopilot is designed to fly the airplane during the landing approach and right onto the runway. Simulated autopilot malfunctions are introduced during the test program to prove that the pilot can always recognize and compensate for a problem should it occur at any point during the landing. Hundreds of automatic landings were conducted during the test program.
The stalls are done for performance, and stalls are also done for what we call characteristics. In characteristics, we have to show, and these are tests that must be certified, that the airplane is controllable in stalls or recoverable in stalls. In general, the characteristics are excellent on this airplane. For an airplane of such tremendous size, it's almost impossible to describe what a gentle and fully controllable stall that we have.
During a flight test program such as the 747, there are as many as 500 stall tests conducted.
We try to appreciate the operational environment that the airlines put the airplane into. In so doing, we try to find that condition, like we look for 35 to 40 knot crosswinds, which is a rarity in actual operation. We're looking for the strong crosswinds, and we're probably going to have to travel around the United States. Right now we have one airplane standing by. The minute we get a report that there are strong crosswinds, he's going to go. That's his first priority.
We finally found one in our own backyard, right in Walla Walla, Washington.
We've always established team philosophy, working on the test airplanes and treating that as though the airplane becomes part of them. You often see the men out there shining up the airplane or their particular engine or so on and so forth. When a man assumes ownership of an airplane, then they take on the responsibility of taking care of it. We had a game going on here between 5 test airplanes. Which airplane could outdo the other? Each team knew that they wanted to go to the remote base and take on certain jobs.
The VMU tests determine the maximum performance of the aircraft in the takeoff configuration. They're performed by placing the tail section of the aircraft in contact with the runway until the airplane lifts off. The speed at which it lifts off is called the minimum unstick speed, or VMU. So the VMU then determines basically the takeoff performance of the aircraft. It also determines the ability of the airplane to tolerate inadvertent abuse. In the case of the 747, it's impossible to abuse the airplane enough so that it doesn't lift off cleanly with very good flying qualities.
Number one airplane conducted shimmy testing in the nose gear linkage systems. We simulated the wear by having the links machined down to where we could put washers in to take out the slop. We just took the washers out, and now we had a free play in the linkage system. And we proved the airplane is shimmy-free, and the airlines then have a maintenance requirement that they'll watch.
Of adverse conditions that have to be simulated. Operation from wet runways, for instance. The Bon-Ami doesn't make a very smart paint job, but it'll sure tell us all we want to know about spray patterns.
First of all, the Boeing shop supervisor signs the airplane as being ready for the test. Then the Boeing inspection department verifies this, signs the release. And then the Boeing flight test engineer in charge of that airplane signs it off, which means that our engineering department agrees that the airplane is in proper configuration for the test that we're going to perform. Then the FAA inspector signs it, and then that's ready for the pilot, and I merely sign it off as sort of a formality.
When you get in the airplane, it does seem very high up. Your eye level's approximately 27 feet high above the ground. However, you've got very good visibility looking down, so you can see very close to the nose of the airplane. As far as taxiing, it's much easier than, say, a 707 to taxi. After taxiing around for a little bit, or even the landings or the takeoffs, it seems very normal, and the other airplanes seem like they sit too close to the ground. This seems like it's just the right height. On the spray testing, we made 2 runs at 30 knots, one at 50 knots, one at 75 knots, and one at 100 knots. The spray trough was approximately 8 feet wide, 70 feet long, and it had a half an inch of water in it. We're looking for any impingement of water on the air conditioning inlets around the static ports of the airplane, and make sure we don't have any ingestion from the nose wheel spray going into the engine inlets.
Other adverse weather conditions include simulating ice buildup on the airplane.
We put on simulated ice shapes, which are fabricated plastic shapes that look like the worst possible ice configuration, and then the airplane is installed and also find out if the drag is significantly different. And usually the natural icing has always been less severe than our simulated icing test that we do with these shapes.
After a time, you become pretty well convinced that you've found all there is to know about an airplane. That is, you and your own people do. And when you welcome the FAA administrator, the man that's bringing that vital paper in his pocket, you know you've hit pay dirt.
The final type board meeting resulted in signing of the airplane flight manual, the production certificate, and the type certificate in the one meeting, which is a first for a final type board meeting. The airworthiness certificate has since been issued for the first airplane to be delivered with a full type certificate.
Thank you, George. Joe, may I have the production certificate? And Earl, could I have the vellum for the airplane flight manual, please? You know, a stroke of the pen doesn't take very long, but it sure is a big stroke, really. I did sign the airplane flight manual there. I'm going to sign now the production certificate and the production limitation record. This concludes the final flight certification board for the Model 747.
Thank you all.
The outcome of this effort is that we find the Boeing 747 as meeting or exceeding the safety standards developed from the experience of the Federal Aviation Administration. As a result of this effort, which included some 1,500 hours of test flying, we are convinced this airplane meets or exceeds the standards for safety evolved in civil aviation history. We therefore recommend the Boeing 747 receive the FAA type certificate.